So let's look at the definition of a continuity at a point, and we're going to actually look at a few examples to see if we can see what types of discontinuities we have in these few examples. So remember that a function f is continuous at a number a if the limit as x approaches a of f of x is equal to f of a. And in writing that equation, we have to keep in mind that writing that equation assumes that the limit as x approaches a of f of x exists as a finite number, and that f of a exists as a finite number, and that those two numbers are equal to each other. So there's three sort of ways that a function can fail to be continuous at a number a. If the limit doesn't exist, or if the output doesn't exist for if a is not in the domain of f, or if those two values are not equal to each other. So let's take a look at a few examples, and remember there are three different types of discontinuities, and I just put these up so that we can kind of label them. So here's a type of discontinuity. What type of discontinuity do you see here? Little quiz. Okay, so as we're coming through taking different x values, different input values, we can see that the output values seem to be coming in negative, and then they become positive, and then all of a sudden the output value jumps at x equals 3. So what we have here is a jump discontinuity at x equals 3. How about this example? This is the one where we have the limit exists at x equals negative 3. Okay. The limit as x equals negative 3 appears to be, I don't know, 2.5 or something. But the function is not defined at x equals negative 3. So this violates the definition of limit in that case. In here, we call this a removable discontinuity. Okay, and the reason why this is, well, one way to think of this being a removable discontinuity is like if we are kind of traveling along with new inputs to f, we come along and the outputs seem to be going in some continuous fashion, okay, some predictable manner, and then all of a sudden there's a blip and like the function doesn't exist at x equals negative 3. But if you're kind of watching this as a movie, then as those input values are traveling along, it's like if you were to blink, you would miss the discontinuity. Separate from if you were looking at this one, if you're going through the input values and paying attention to the outputs, then if you blink right at x equals 3, then you're still going to open your eyes and see that you're in a different place. So the removable discontinuities are sort of like if you blink and miss it, then that's a removable discontinuity. And we'll say more later about what that removable discontinuity actually means. Okay, and how about this one? So in this case, we have the limit of the function exists as x equals 2, and the value of the function exists at x equals 2, but the limit as x approaches 2 and the value of f at 2 are not the same. So we have a discontinuity at 2, and again, if we're kind of traveling along the inputs and paying attention to the outputs, if you blink when you get to x equals 2, then you're going to miss the discontinuity. This is a removable discontinuity again. All right, next. How about this one? This is one where if you're going along the input values and you get close to x equals negative 6, all of a sudden there's this infinitely large values. All that matters is that one of the one-sided limits is infinite. So the limit as x approaches negative 6 from the right of this function is positive infinity. So this is an infinite discontinuity. Now here's a question. There's a concept of continuity from the left and continuity from the right. And can we actually see which ones are continuous from the left and which ones are continuous from the right at the specific input variable? So let's look back at example 1. And so this one, it's a jump discontinuity, remember. I'm just going to label that. Jump discontinuity, which means that the left-hand limit, the limit as x approaches 3 from the left, is different from the limit as x approaches 3 from the right. And the idea of the continuity, the left-handed continuity or the right-handed continuity, is which one of these one-sided limits actually equals the value of the function at x equals 3. So here, it looks like the limit as x approaches 3 from the left is somewhere around 1. And the limit as x approaches 3 from the right is like -2. But then the value at x equals 3, the output value at x equals 3 is -2. So this function would be continuous from the right, but not continuous from the left at x equals 3. Put that down. Let's look at this. So anytime you have the hole in the graph thing, this function is going to be not continuous from the left or the right, because continuous from the left or the right means that one of those one-sided limits has to equal the value of the function at that point. But these removable discontinuities, the removable discontinuities always have a limit that is a two-sided limit. So that means if it's a discontinuity, that means that the function is not at that place where that limit exists. So this is neither continuous from the right nor the left. And this one, again, removable discontinuity, and it's not continuous from the left, it's not continuous from the right, because the limit as x approaches 2 of this function looks like around -3, but the value, the output value, is actually 2. Let's look at example 4. This function, remember, it has an infinite discontinuity at x equals -6. Go ahead and think about, is this function continuous from the left or continuous from the right, or neither at x equals -6? Now you can see as x approaches -6 from the left, it looks like the limit, the left-hand limit, is around 3. As x approaches -6 from the right, it looks like the right-hand limit is positive infinity. And the actual value of the function is 3, so it looks like that output value is equal to the left-hand limit. So this function would be continuous from the left at x equals -6. It is worth noting that all of these functions are continuous at every number in their domains. Okay, so if a function is continuous at every number in its domain, then we call it a continuous function. So all of these functions are continuous, are continuous functions. And you might notice that this is a restatement of the direct substitution law from section 2.2, which just means that if you want to take the limit as x approaches some number, and that number is in its domain, then the limit is equal to the function value at that number. Okay. Okay, so this says all of the functions in our standard catalog are continuous functions. That might feel a little bit counterintuitive, considering some of these functions do have discontinuities, such as like the tangent function has an infinite discontinuity at x equals pi/2. However, it is important to see that it's continuous at every number in its domain, and pi/2 is not in the domain of the tangent function. So that still fits, as the tangent function is still continuous at every number in its domain.